Hi, I'm Professor Verkler, and today we're talking about diodes and LEDs. We're going to learn about how to tell whether a diode is on or off, how to use resistors to limit the current, and then how to control the brightness of an LED with these current limiting resistors. So light emitting diodes are a special type of diode that emit light when they're on. We can use different materials to get different colors of LEDs, and they usually come in this plastic casing shown on the left there. That'll help kind of direct the light out in one direction. So how does a diode or LED work? So we actually have a crystalline material, a semiconductor material, and then we actually dope it, which means uh, we add atoms of a different type to change the properties of the material slightly, but we add just a small amount of those percentage-wise. And so we'll add to one side, we'll add a type of atom that will add extra free electrons to the crystalline structure. And then on the other side here, the p-doped side, we will add atoms that will actually create the opposite of that. So they're called positive kind of holes without electrons. So we have these two different materials nested next to each other. And then when we apply a voltage, so if we apply a positive voltage here, the negatives on that side, then we naturally have this force wanting to push these positive charges that way, or the electrons this way, where they'll connect together in that middle region. And when they recombined, it will create light in the case of the LED. In the opposite way, if we apply a voltage in the other direction, over here on the right corner, so we are applying that positive voltage on the n-doped side. Now we have electrons that are like wanting to go this way, and these positive charges wanting to go that way based on the voltage applied to them. So we're actually increasing this depletion layer, as it's called, in the middle, and things can't get across, so current will not flow. So we call this voltage the forward voltage that you need to really turn that diode on. So a diode can be thought of as a one-way street, and the current only flows this way in the direction of that arrow on it. And then you notice on the previous page, I also had a symbol like this with two arrows coming off. The arrows represent light coming off. So that would be the circuit symbol for an LED. So here's what some physical actual diodes look like. So we've got LED over here, and these are directional items, right? The direction matters, meaning I don't want to mix up which is which when building my circuit. So we have this shorter leg here, which represents the negative side, or this side of the diode. And then there's also a notch here on that round cap, a flat side to that round cap that will also indicate the negative side of your diode in case the legs got cut off here or something. And not all diodes are LEDs. So we have other diodes that don't emit light. They're generally made of silicon, and as a result, their forward voltage is generally 0.7 volts. And we draw a line here on their packaging to indicate that negative side again. So another way to think about this would be the IV curve for an LED or diode. So this is the first nonlinear device that we're working with. And as you can see, it has something that looks somewhat like an exponential curve. So we can see the forward voltage labeled here, which is that point at which the current really starts going up. And depending on the color, we have different forward voltages, anywhere from 1.6 to about 3.5 in this picture here. So I don't really want to do calculations using an exponential equation. So we are going to create a simplified model for these diodes. So this exponential curve here can be approximated then as a straight line here until the forward voltage, and then at the forward voltage, a vertical line. I like this model because it's much simpler to work with. So if I'm below the forward voltage, it's just going to be off. It's going to act as an open circuit. And then if I hit the forward voltage, it's going to be fixed at that forward voltage. And it'll act like a voltage source. If you remember back to when we learned about IV curves, there were these vertical lines we were drawing like this for the ideal voltage sources. Now we're going to work through some basic examples of how to apply that. So here is a 1.2 volt supply connected to a diode. So this is a basic diode, not an LED. So 0.7 volts would be our forward voltage. So it should turn on, right? Well, yes and no. So if I replace this with a 0.7 volt supply, now I've got two things attached to each other in parallel that are different voltages. And we learned recently that's a bad idea, right? We're going to have a lot of current flowing and maybe break something. So we shouldn't ever do that. We should always have a current limiting resistor in the circuit. So let's calculate the current for this second situation. So again, the forward voltage is 0.7 volts. The current looks like it's flowing in the right direction for this diode to turn on. So we'll replace it with this voltage source. And now I can use Ohm's law. I see I have nodal voltage wise 1.2 volts on this side and 0.7 volts on this side of the diode. So using Ohm's law, I is equal to V over R. Then I have 1.2 minus 0.7 over 1 kilo ohm, which is equal to 0.5 volts over 1 kilo ohm, which is equal to 0.5 milliamps. Now, what would happen if I had 500 ohms here as the resistor instead of 1 kilo ohm? Well, let's go down and look at our math. So the only thing that's changing is this 1 kilo ohm, right? So now we have 0.5 volts over 500 ohms, which is the same thing as 0.5 kilo ohms. So I get 1 milliamp. Whenever I have a K down here in the bottom, when I divide by a K, that creates an M at my output. That's how I remember the math quickly in terms of my units. So let's also sanity check this. This is a linear equation. So when I halved the resistance, I better have doubled the current, and I did. Yay. So what's going to happen differently? If this was an LED, let's say, draw little arrows there to represent an LED. Well, the more current that flows, the brighter my LED is going to get. Okay, and finally, we're going to look at this case where we have two LEDs, or I guess in this case maybe diodes, we'll say, in series. So if they're the basic diodes that are 0.7, if they're both on, they'd both be 0.7 volts, which would add up to 1.4 volts together. But that's more than my voltage supply here. So that means they can't be on. So these are actually off and no current flows. In the next section, we'll do more practice problems about how to solve circuits with diodes and see some examples of useful circuits that use diodes.